the end of Nand2Tetris hardware part. From the NAND gates, we've been able to create basic logic gates all the way up to large complex components. Now it's time to create the final building blocks, the memory and the CPU, and combine them to build the final hack computer. We start with the memory. The memory includes not only RAM but also the screen and keyboard, which are accessed like any other memory locations using addresses. RAM occupies addresses from 16-bit hex values 0x0000 to 0x3FFFF, from 0x4000 to 0x5FFFF lie the screen pixel registers. Finally, 0x6000 holds the keyboard register, which contains the value of the currently pressed key. To understand how these addresses map to the appropriate memory devices, we, as always, construct a truth table. Since the address is 15-bit, bit 15 is ignored. If bit 14 is 0, the device is always RAM. If bit 14 is 1 and bit 13 is 0, the device is the screen. If both the bit 14 and bit 13 is 1 and all remaining bits are 0, the device is the keyboard. And if any of the remaining bits is 1, the address is invalid. To streamline this table, we only need bit 14, bit 13 and the OR of the remaining 13 bits to detect any one in the lower bits. For the memory output, we can think of this as selecting one of several 16-bit devices using 3 bits. This is exactly the behavior of a MUX 8x16, where the output of the selected device becomes the output of the memory. While the device can output values at the same time, for memory input, only one device will receive the load signal. The keyboard is a read-only device. It cannot be returned to, so its load signal is always invalid. Only RAM and screen are writable. If we include the load input in our truth table and simplify, we see a pattern where 2 bits route a single input signal to different outputs. This matches the behavior of a DMUX 4-way, with the outputs going to the load signal for RAM and the screen. Now we are ready to create the memory in STL. We add the RAM, screen and keyboard components. Both RAM and screen receive the same input in. They also receive the same lower address bits depending on the individual input sizes. From the load signals, we use a DMUX 4-way with the memory's load as the input and the 2 upper address bits as selectors. The first 2 outputs are for RAM, the third output is for the screen, the fourth output is unused, so disconnected. To feed RAM's load signal, we OR the first 2 output together using an OR gate. The third output goes directly to the screen's load input. For the output, we use a MUX 8x16 chip. The first 4 inputs are for RAM, the next 2 inputs are for the screen, the 7th input is for the keyboard, the 8th input is simply 0, representing an invalid address. To select among these, we need to detect which device is being addressed. We chain 2 OR 8-way gates to OR all the lower 13 address bits, and along with the address bit 14 and 13, we use this to build a 3-bit selection signal for the multiplexer. The output of the MUX 8x16 becomes the final memory output. Finally, we execute the test to verify this implementation. Now we can move on to the CPU that parses and executes the 16-bit instructions according to the specifications. Let's look at the instruction bit by bit. First up is bit 15, which determines the instruction type that can directly control the internal A register. If the bit is 0, it is an A instruction where the internal register A is loaded with the instruction itself as the value. If the bit is 1, it is a C instruction where the remaining instruction bits define execution behavior involving an ALU. The ALU's X input is always the internal D register, but the Y input can come from either the A register or from the memory location addressed by the A register's value. Bit 12 selects this Y input. It chooses between the output from the A register and the value from external memory addressed by A. The next 6 bits, bit 11 to 6, are commands to the ALU, telling it which operation to perform on the inputs to produce the output. Then the next 3 bits, bit 5 to 3, can optionally direct the ALU output to different destinations. Bit 5 enables loading of the A register, but only for C instructions, since A register loads the instruction itself during an A instruction. Bit 4 enables loading of the D register with the ALU output. Bit 3 enables writing of the ALU output to the external memory. The final 3 bits 2 to 0, optionally affect the program counter. They specify a condition on the ALU output which, if true, causes the PC to load the value stored in A, effectively jumping to that instruction address. Now we try to recognize patterns using a truth table again, starting with the A register. When I is 0, load is always 1 and input is always the instruction. When I is 1, if D1 is off, input does not matter. If D1 is on, input must be the ALU output. We can set the don't care input to the ALU output and describe this behavior as a multiplexer. The I bit selects between 2 different values for both load and input. For the D register, the load is only enabled when if it is a C instruction and D2 is enabled. This behavior resembles an AND gate for the load signal. We can safely set all don't care inputs to the ALU output. The same applies to writing to memory, which depends on the D3 bit. As for the ALU, we can configure the don't care states to behave like a C instruction. The I bit no longer matters here. The A bit selects between the A register output and memory output, making this a MUX16. Now, for the hardest part, the jump logic using the program counter. The ALU also provides 2 status outputs, whether the result is 0 and whether the result is less than 0. These can indicate whether the result is less than, equal to, or greater than 0. A simple NOT operation on the result can derive the other jump conditions. One possible implementation: use a demux 4-way and NOT gates to derive signals for each condition the output satisfies. Use a demux 8-way to determine which condition the instruction specifies. Perform AND on each satisfied condition with its corresponding instruction bit. Perform an OR on all the results to get the final jump condition. Finally, AND this with the I bit to ensure the jump only occurs during a C instruction. This solution works perfectly but is verbose and uses many lines or components. To simplify, we can try to find a smaller Boolean expression using a K-map. Starting with the truth table using 5 inputs, only list true conditions to keep it manageable. Build a K-map and derive the minimal Boolean expression. Reorganize the inputs to identify a multiplexer pattern which reduces component usage. In any case, since the load signal takes priority, the increment signal for the program counter can always be kept on and its input always set to the A register. Now let's build the CPU chip in SDL. First of all, I'm using 2 NOT gates for each instruction bit to make them easier to identify. Next, we include the A register. A multiplexer will generate its load input and MUX16 will generate its data input. Then we add the D register and its load signal will be generated using a simple AND gate. The write signal for the external memory will also be generated in the same way using an AND gate. Now we add the ALU. Its X input will come from the D register output. For the Y input, a MUX will select between the A register output and the data from external memory. The 6 compute bits from the instruction will be mapped directly to the ALU's function inputs. The ALU's outputs serve both as the CPU's output and as the input to the external memory. Finally, we add the program counter. The PC's output becomes the CPU's program counter output, which addresses the external ROM. For loading the PC, we'll use MUXes and logic gates to implement the sum of products logic based on the jump condition bits and the ALU status outputs. We'll use an AND gate as before to ensure that the PC is loaded only during C instructions. Its data input will always be the A register output. The INC signal can always be set to true. Since the load signal takes priority, the CPU's reset input is directly connected to the PC's reset, and then we run the test. To create the final hack computer chip, all we have to do is include the ROM, the CPU and the memory and interconnect them appropriately.